Table 450.3 in the National Electrical Code, referred to as NEC, establishes the maximum rating or setting for overcurrent protection devices used with transformers. This is based on both the impedance of the transformer and its voltage rating. For transformers operating at over 600 volts and possessing an impedance greater than 6%, the NEC permits a maximum overcurrent protection setting of up to 600%. The primary reason for allowing such a high maximum setting stems from the behavior of high impedance transformers during fault conditions. These transformers exhibit a significant voltage drop when a fault occurs. This voltage drop inherently limits the magnitude of the current that can flow through the transformer, even under severe fault scenarios. Consequently, high impedance transformers do not necessitate protection against the same level of fault current as transformers with lower impedance values. It's crucial to understand that the NEC maximum setting of 600% for overcurrent protection might not always seamlessly align with the transformer's allowable through fault current duration. Standard C57.109-1993 provides essential guidelines for calculating the allowable through fault current duration for a transformer. This calculation considers factors such as the transformer's insulation system and the anticipated duration of the fault. If the overcurrent protection is set too high, the transformer could be exposed to a fault current duration that exceeds its design limits. This could potentially lead to degradation or damage to the transformer's insulation system, reducing its lifespan and reliability. To achieve proper coordination between the overcurrent protection and the transformer's allowable fault current duration, it is recommended to follow a structured approach. Firstly, calculate the allowable transformer through fault current duration. Employ standard C57.109-1993 to determine this duration, considering both the transformer's insulation system and the maximum anticipated fault current. Secondly, determine the maximum setting for the overcurrent protection. Set the maximum setting of the overcurrent protection device to a value that remains below the allowable fault current duration calculated in the first step. This might necessitate using a lower maximum setting than the 600% permitted by the NEC to ensure adequate protection. Thirdly, confirm coordination. Verify that the chosen overcurrent protection setting effectively coordinates with the transformer's through fault current duration capability. This verification process helps ensure that the protection system will operate correctly to protect the transformer from damage. By adhering to these steps, one can ensure that the transformer receives adequate protection against fault currents, while simultaneously preventing damage that could arise from excessive fault current duration. This approach balances the requirements of the NEC with the specific characteristics and limitations of the transformer, leading to a safer and more reliable electrical system. When applying these principles, it is important to consider several additional factors. These include the specific type of overcurrent protection device being used, the transformer's loading profile, and the overall system configuration. Different types of overcurrent protection devices, such as fuses and circuit breakers, have varying operating characteristics that must be taken into account. The transformer's loading profile, which describes how the transformer is typically loaded over time, can also influence the selection of the appropriate overcurrent protection setting. Finally, the overall system configuration, including the presence of other protective devices, must be considered to ensure that the overcurrent protection coordinates effectively with the rest of the system. In summary, while the NEC permits a maximum overcurrent protection setting of up to 600% for transformers operating at over 600 volts with impedance greater than 6%, it is crucial to coordinate the setting with the transformer's allowable through fault current duration. By following the steps outlined above and considering the additional factors mentioned, one can ensure that the transformer receives adequate protection against fault currents, while also preventing damage due to excessive fault current duration. Understanding the interaction between these standards and guidelines is key to designing and maintaining safe and reliable electrical power systems. The 600% allowance in the NEC exists primarily to accommodate the inrush current experienced by transformers upon energization. This inrush current can be many times the transformer's rated current and lasts for a very short duration. A lower overcurrent protection setting would likely trip during this inrush, causing nuisance tripping and disrupting power supply. However, this allowance comes with the responsibility of ensuring that the transformer is still adequately protected against sustained fault current. Therefore, a careful balance must be struck between allowing for inrush current and providing adequate fault protection. The standard C57.109-1993 is essential for determining the withstand capability of the transformer through fault currents. This standard considers factors such as the transformer's kVA rating, voltage, impedance, and insulation type. By using this standard, engineers can determine the maximum fault current and duration that the transformer can withstand without damage. This information is then used to select the appropriate overcurrent protection setting. It is also important to consider the upstream protection devices when coordinating overcurrent protection. The upstream devices should be sized and coordinated such that they provide backup protection in case the primary overcurrent protection fails to operate. This ensures that the transformer is still protected even if the primary protection fails. The coordination of overcurrent protection is a complex process that requires a thorough understanding of electrical power systems and protection principles. It is recommended that a qualified electrical engineer be consulted to ensure that the overcurrent protection is properly coordinated and that the transformer is adequately protected. Neglecting proper coordination can lead to transformer damage, equipment failure, and even safety hazards. Therefore, it is essential to take the time to properly design and coordinate the overcurrent protection system. Furthermore, it is imperative to regularly inspect and test the overcurrent protection devices to ensure that they are functioning properly. This includes verifying the trip settings, testing the operation of the devices, and inspecting for any signs of damage or wear. Regular maintenance and testing are crucial for ensuring the continued reliability of the overcurrent protection system. It's also essential to document all overcurrent protection settings and coordination studies. This documentation should be readily available to maintenance personnel and engineers for reference. Accurate documentation is essential for troubleshooting problems and for making informed decisions about overcurrent protection settings. In addition to the IEEC and standard C57.109-1993, other standards and guidelines may be applicable to overcurrent protection of transformers, depending on the specific application and location. It is important to be familiar with all applicable standards and guidelines to ensure compliance and to provide adequate protection. Advances in technology have led to the development of sophisticated overcurrent protection devices that offer enhanced features and capabilities. These devices can provide more accurate and reliable protection than traditional devices. Examples of these advanced devices include microprocessor-based relays and intelligent electronic devices. These devices can provide features such as adaptive protection, which adjusts the overcurrent protection settings based on the operating conditions of the transformer. They can also provide advanced communication capabilities, which allow them to be integrated into a supervisory control and data acquisition, also known as SCADA system. These advanced features can improve the overall performance and reliability of the overcurrent protection system. When selecting overcurrent protection devices, it is important to consider the specific requirements of the application and to choose devices that are appropriate for the task. This includes considering factors such as the voltage and current ratings, the interrupting capacity, and the operating characteristics. It is also important to choose devices that are reliable and that have a proven track record. The overcurrent protection of transformers is a critical aspect of electrical power system design and operation. Proper overcurrent protection is essential for preventing transformer damage, equipment failure, and safety hazards. By following the guidelines and recommendations outlined above, one can ensure that transformers are adequately protected and that electrical power systems operate safely and reliably. The principles of overcurrent protection extend beyond just the transformer itself. It's crucial to consider the entire system, including upstream and downstream equipment, to ensure a coordinated and effective protection scheme. This involves analyzing the fault current paths, calculating fault current magnitudes, and selecting protective devices that will operate selectively to isolate faults without disrupting the entire system. Selective coordination is a key concept in overcurrent protection. It means that the protective device closest to the fault should operate first, while upstream devices remain in service to provide backup protection. This minimizes the extent of the outage and allows the rest of the system to continue operating normally. Achieving selective coordination requires careful selection and setting of overcurrent protection devices. It also requires a thorough understanding of the system's impedance characteristics and fault current behavior. Computer-based modeling and simulation tools are often used to analyze fault currents and to verify the coordination of overcurrent protection devices. These tools can help engineers identify potential coordination problems and to optimize the protection scheme. In addition to selective coordination, it is also important to consider the sensitivity of overcurrent protection devices. The devices should be sensitive enough to detect and respond to relatively small fault currents, but not so sensitive that they will trip unnecessarily due to normal system disturbances. Striking the right balance between sensitivity and stability is a key challenge in overcurrent protection design. Another important consideration is the impact of overcurrent protection on system reliability. While it is essential to protect equipment from damage, it is also important to minimize the frequency and duration of outages. Overcurrent protection schemes should be designed to minimize the risk of nuisance tripping and to allow for rapid restoration of service after a fault. This may involve using advanced protection techniques such as adaptive protection and fault location. Adaptive protection adjusts the overcurrent protection settings based on the operating conditions of the system. This can improve the sensitivity and stability of the protection scheme and can reduce the risk of nuisance tripping. Fault location techniques can help to quickly identify the location of a fault, which can speed up the restoration of service. In addition to the technical aspects of overcurrent protection, it is also important to consider the regulatory requirements. Electrical codes and standards often specify minimum requirements for overcurrent protection. It is essential to comply with these requirements to ensure the safety of personnel and the public. Overcurrent protection is a dynamic field that is constantly evolving. New technologies and techniques are being developed all the time. It is important to stay up to date on the latest advances in overcurrent protection to ensure that electrical power systems are adequately protected. This may involve attending conferences, reading technical publications, and participating in training courses. The proper overcurrent protection of transformers is a complex and challenging task that requires a thorough understanding of electrical power systems, protection principles, and regulatory requirements. By following the guidelines and recommendations outlined above, one can ensure that transformers are adequately protected and that electrical power systems operate safely and reliably. It's a continuous learning process that demands dedication and attention to detail. Furthermore, consider the aging infrastructure in many electrical systems. As equipment ages, its performance can degrade and the risk of faults increases. Overcurrent protection schemes should be reviewed and updated periodically to ensure that they are still adequate for the current conditions. This may involve replacing old overcurrent protection devices with newer, more reliable devices. It may also involve re-evaluating the overcurrent protection settings to ensure that they are still appropriate. When upgrading overcurrent protection, it is important to consider the compatibility of the new equipment with the existing equipment. This may require using adapters or other interface devices. It is also important to ensure that the new equipment is properly tested and commissioned before it is put into service. Overcurrent protection is not just a matter of selecting and installing the right equipment. It is also a matter of ensuring that the equipment is properly maintained and operated. Regular inspections and testing are essential for ensuring that overcurrent protection devices are functioning properly. Maintenance personnel should be trained to recognize potential problems and to take corrective action. In addition to regular maintenance, it is also important to have a well-defined emergency response plan in place. This plan should outline the steps to be taken in the event of a fault or other electrical emergency. The plan should include procedures for isolating the fault, restoring service, and investigating the cause of the fault. Effective communication is essential during an electrical emergency. All personnel involved in the emergency response should be able to communicate with each other clearly and effectively. This may require using radios, cell phones, or other communication devices. The overcurrent protection of transformers is a shared responsibility. Electrical engineers, maintenance personnel, and operators all have a role to play in ensuring that transformers are adequately protected. By working together, these individuals can help to prevent transformer damage, equipment failure, and safety hazards. In addition to the technical aspects of overcurrent protection, it is also important to consider the human factors. Human error can contribute to electrical accidents. It is essential to train personnel to work safely around electrical equipment and to follow proper procedures. Safety training should be provided on a regular basis. Personnel should also be encouraged to report any potential safety hazards. A strong safety culture is essential for preventing electrical accidents. A safety culture is one in which safety is valued and promoted at all levels of the organization. In a safety culture, personnel are empowered to identify and correct safety hazards. They are also encouraged to speak up if they see something that is not safe. The overcurrent protection of transformers is an ongoing process that requires continuous improvement. By learning from experience and by staying up to date on the latest advances in technology, one can continuously improve the overcurrent protection of transformers. This will help to ensure that electrical power systems operate safely and reliably for years to come. Overcurrent protection is an investment in the future. By investing in proper overcurrent protection, one can protect valuable equipment, prevent costly outages, and ensure the safety of personnel and the public.